Chapter 17, Equilibrium, the extent of chemical reactions. As we already know, most reactions reach equilibrium. For example, A goes to B. Okay, and if you let the reaction proceed for a long time, the reaction eventually will reach equilibrium. So let's say at equilibrium you have 2 molarity A, 3 molarity B. So this is the equilibrium concentration mixture, and the K can be calculated to be 3/2. All right, so however, if you add, okay, let's say you add 1 molarity A into the system. Now, in the system, you have 3 molarity A and 3 molarity B. And the Q will be 3 divided by 3, which is not K. And that means the system is not at equilibrium anymore. And therefore, the reaction will continue, either go forward or go reverse until the new Q equals K. In other words, the reaction will reach the equilibrium again, a new equilibrium again. Okay. So how do you know the reaction go forward or go reverse? This is summarized by the Châtelier principle. Okay, it says when a chemical system at equilibrium, so this is at equilibrium, is disturbed. So this is disturbed. You add more A. The reaction not at equilibrium anymore. It re-attains equilibrium by undergoing a net reaction. So either go forward or go reverse. That reduce or counteracts the effect of disturbance. Okay, this is the key of this principle, and we'll explain in detail in the next slide. Okay, but first let's look at some more concepts. All right, so let's erase that. Okay, so a system is disturbed when a change in condition. So in changing, in our example is adding A concentration. That's the change in condition, force it temporarily out of equilibrium. The system responds to a disturbance by shift in the equilibrium position. A shift to the left, so the reaction may go left, which will consume product to form reactants, or it may go to the right, all right, from reactants to form the product. Okay, in any event, it will reduce or counteracts the effect of disturbance. All right, we'll explain in the next slide. Let's explain how the Châtelier principle works. So the reaction A goes to B, and at the equilibrium you have 2 molarity A, 3 molarity B. And now you have a disturbance, and that is you add A into the system, so A increase. That's the disturbance. According to the Châtelier principle, the reaction will respond by reduce the disturbance or counteracts the disturbance. And that means the system will try to decrease A. Okay, because disturbance you increase A, so the system will try to decrease A. So which direction can decrease A? Go forward. Okay, if reaction go forward, A will be consumed, B will be formed. So that will decrease A, counteracts or reduce the disturbance. So if reactants is added, equilibrium position shift to the right side. Right side means forward reaction that consumes A. On the other hand, if a product is added, so B increase is a disturbance, the reaction will respond by go left. Okay, what go left is the reverse reaction, and the reverse reaction will reduce B. B is the reactants for the reverse reaction, consumes B, increase A. Okay. On the other hand, if A decrease, Okay, if you decrease A, so how does the reaction go? Well, A is reactance. If you decrease A, the reaction will respond by counteracts or reduce the disturbance by increase A. Okay, it needs to increase A. How does it do? It will go reverse. Left side, because left side will increase A. So if reactance is removed, the equilibrium position shift to the left side. Okay, again, when the reactance is removed, that's a disturbance. The system will try to increase it, and that's the left reaction. If product is removed, so if you reduce B, okay, the reaction will go forward. That will increase B. Okay, so always remember that the key word is reduce the disturbance or counteracts the disturbance. All right. So here, only substance that appear in the expression for Q can have effect. And this is because, as we explained, the reaction change, when you change a condition, particularly the concentration, Q change so that the Q is not K anymore. And that's the driving force for the reaction to shift position until a new Q becomes K. The reaction reaches a new equilibrium. But if a substance does not affect Q, then it will not have any effect, okay, when the disturbance is added to the system. And the change in concentration has no effect on the value of K. All right, K doesn't change. It's the Q change. When you change concentration, you have a disturbance. Q change. Q is not K, and therefore the reaction shift. But the K remains the same. For this reaction, the following factors will cause the reaction to shift to the right side. Increase reactance. If reactance concentration are increased, the reaction go to the right to decrease the concentration of reactants. Or if you remove the product from the system. So if you remove some product from system, the reaction will shift also to the right so that more product will be formed. On the other hand, these are the factors that will cause the reaction shift to the left side. So if you remove the reactants, decrease concentration reactants, the reaction shift to the left side to produce more reactants. Or if you add a product into it, okay, if you add a product, the reaction shift to the left side to consume it. Let's do some quantitative calculation to show the Châtelier principle. Let's use this reaction as an example. And initially, we have a mixture already reached equilibrium. So this is an equilibrium concentration mixture. Okay. Now we have a disturbance. So some chlorine is added, 0.075. All right. Now after disturbance add, the reaction will shift direction until it reaches equilibrium. And we can calculate at new equilibrium what are the concentrations. Okay, can you try it? You already learned you need to write a reaction table. Okay, so you can pause anytime, try it. Now here is what we are going to do. Okay, here is the new initial concentration after disturbance. Phosphorus trichloride is still 0.2, but the chlorine becomes 0.2 because 0.125 plus this one, disturbance, okay, you added it. So the new concentration becomes 0.2 and the product is still 0.6. So note that this increase, okay, after disturbance. All right, is this equilibrium? Of course not, because if this is equilibrium, this can't be. All right, so they must change. So let's assume change is X. For the reactants is negative, for the product is positive. New equilibrium should be 0.2 minus X, and here 0.2 minus X, and the product should be 0.6 plus X. Okay, so how do you solve X? All right, if you know equilibrium constant, then you can solve X. Because we know this is equilibrium mixture, so from this you can calculate K. K is 0.6 divided by 0.2, 0.125. That's the equilibrium constant. And this should equals to this 0.6 plus X divided by 0.2 minus X times 0.2 minus X. Okay, so this equal to K, and you can solve X. All right, you have done many questions, sample questions, so you should be familiar with this procedure now. So let me give you the answer. X is 0.037. All right, and you can see here this is the experimental data. Okay, experimental data is when equilibrium when the reaction reach new equilibrium is 0.637. So if we use 0.6 plus the calculated 0.037, and you get 0.637, and that matches experiment data perfectly. All right, so our calculation is right, is very consistent with experiments. Okay, now let's look at the concentration at new equilibrium. At new equilibrium, the reactant phosphorus trichloride is 0.2 minus 0.037, and that is smaller than 0.2. You minus 0.037. Okay, so that means the reactant decrease concentration. All right, so this decrease. All right, now what about the chlorine gas? Chlorine gas 0.2 minus 0.07 also decrease from the new initial 0.2. So reactants decrease. The product increase because 0.6 plus 0.037 becomes 0.637. So it increase. Okay, and therefore when you have a disturbance to increase the reactant, the reaction go forward to reduce the concentration of reactants and to increase the concentration of the product, and that is exactly what the Châtelier principle predicted. Okay, but if you remember during the calculation, K does not change. K here, we use this K to calculate, to apply for the new equilibrium. So K doesn't change. It's the concentration, or Q, changes during the reaction. This diagram shows how the reaction responds to a disturbance. Okay, same reaction, and initially chlorine, phosphorus trichloride, phosphopentachloride at equilibrium. These are the equilibrium concentration. So at this moment, Q equals K because it's at equilibrium. Now at a certain time, there's a disturbance, and you can see the yellow line indicates the concentration of chlorine has a jump, increase. That's a disturbance. Chlorine, the reactant, increase concentration, and at this point, K is not Q. Q doesn't equal to K anymore. Reaction is not at equilibrium, so the reaction will shift, and you can see the reactants concentration start to decrease, and the product concentration start to increase. Okay, you can see the increase. Reactants decrease, product increase, and that is the forward reaction. Okay, so when you increase chlorine, reaction go forward to increase product, to decrease reactants until a new equilibrium is reached, where Q equals K again. Sample problem 17.11. This question is about a reaction between hydrogen sulfide, oxygen, to make sulfur and water. The question is, A, what happens to water? Water is a product if oxygen, the reactant, is added to the system. So how do you predict concentration change when there's a disturbance? Well, we just learned the Châtelier principle, so we can use the Châtelier principle. Now we also learned that if we can calculate Q and compare with K, we can also predict the direction. So in this question, we are going to use two methods. One, the Châtelier principle, and two, we write Q and see how the change of one concentration affect Q and how to change direction so that Q will equal to K again. Let's first apply the Châtelier principle to this question. So if the disturbance is oxygen added, means that you increase oxygen concentration. According to the Châtelier principle, the reaction proceeds to counteract or reduce the disturbance. That means the reaction will go direction to decrease oxygen, and that is the forward reaction, because forward reaction will consume the reactants, at the same time will increase the product, and therefore that gives our answer: the water concentration will increase. Reaction go forward and increase water concentration. Now let's look at Q. Okay, use Q to predict the direction. So first we write equation Q, product divided by reactants, and note that sulfur is a solid, so it's not included. All right. Now in this equation, oxygen, you divide by reactants oxygen. If oxygen increase, okay, that will decrease Q, because you divide by a larger number, the ratio will decrease. All right. Now, so when Q decrease, Q does not equal to K anymore, so the reaction will try to increase Q. So the question is, how do you increase Q? Okay, one way is to increase water, which is a product. The other way is reduce hydrogen sulfide, which is the reactant. So again, by using Q, we can predict that in order to increase Q, because when you add water or oxygen, Q decrease. So Q is not K, less than K, and therefore in order to increase Q, you need to increase product, you need to decrease reactants, and that's the forward reaction. Okay, so Q decrease due to the oxygen is added, and the reaction proceeds to the right until new Q equals K again, and therefore water concentration increase. So both the Châtelier principle and using Q, we get the same answer. Now let's look at B. Now B said same disturbance is oxygen added, so we know the reaction must proceed to the right side. All right, and the question is, what happens to hydrogen sulfide? Hydrogen sulfide is the reactant, so when the reaction go forward, the reactant will decrease. Okay, so again, if you look at the Q, when oxygen added, Q decrease. In order to increase Q, you have to reduce hydrogen sulfide. So again, the answer is hydrogen sulfide decreases. In question C, if hydrogen sulfide is removed, okay, hydrogen sulfide is a reactant, so it decreases reactant concentration. The question is, what happens to oxygen? Okay, oxygen is here, another reactant. So what happens to oxygen? According to the Châtelier principle, if the reactant is decreased, the concentration is decreased, the reaction go reverse so that it will increase it, okay, counteracts the disturbance. So if the reaction go reverse to the left side, oxygen will be produced, so it will increase. So the answer here is increased oxygen concentration. Now let's look at the equation Q. Hydrogen sulfide is a reactant, so it's in a denominator. If you decrease denominator, the ratio will increase. So this Q will increase. Now, originally Q equals K. When Q increases, it becomes larger than K, and therefore reaction is not at equilibrium anymore, and they will in order to re-establish equilibrium, Q has to decrease. Okay, so you need to decrease Q. So how do you decrease Q? Either reduce water, okay, water is the product, or increase reactants. Okay, and therefore we predict again that if hydrogen sulfide is removed, the reaction will go reverse because it will decrease product, increase reactants, and so oxygen concentration will increase. Okay, so when hydrogen sulfide is removed, Q increase because you divide by a smaller number, so reaction proceed to the left until Q equals K again. So because reaction go reverse, so reactants increase, oxygen increase. In question D, if sulfur is added, okay, what happens to hydrogen sulfide? Now, because sulfur in the equation is a solid, the concentration solid is unchanged as long as the sum is present, so it does not appear in reaction quotient. So adding more sulfur has no effect, and therefore hydrogen sulfide is unchanged. The Châtelier principle can be also used to study the effect of pressure on a system of equilibrium. Let's use the same reaction as an example. So phosphorus trichloride represented by blue ball, and chlorine by brown, and phosphor tripentachloride by green ball. So suppose this is a system at equilibrium. We can count how many molecules in the system. In this case, we have 3 blue balls, that's the phosphorus trichloride, and 3 chlorine brown, and 9 green. So total number is 15 molecules in the system. This system is at equilibrium. Now we apply a disturbance, and that is increased pressure. So this is a disturbance. Okay, so how do you increase pressure? One way to do it is to push down the movable wall so that volume decrease. When volume becomes smaller, pressure increase. So what happens to the reaction? Okay, according to the Châtelier principle, if you have a disturbance, the reaction will counteract or reduce the disturbance. The disturbance is increased pressure, and therefore it will go to the direction try to decrease pressure. Okay, so how do you decrease pressure? If the system molecule becomes smaller, fewer molecules, then the pressure will decrease. If we go back to the reaction, 1 molecule phosphorus trichloride plus 1 chlorine forms 1 phosphorus pentachloride. So if reaction go forward, the reactants total 2 molecules. It forms 1 molecule, so 2 becomes 1. Okay, if more reactants forms product, the system will become fewer and fewer molecules, because whenever reaction proceeds, 2 molecules becomes 1 molecule. Okay, and therefore the Châtelier principle predicts that if you increase pressure, the reaction will go forward. More reactants becomes product, and so that the total pressure will decrease. If you count the molecules in this new system, and you will find that now you have 2 molecules of phosphorus trichloride, 2 molecules of chlorine, and 10 molecules of product phosphorus pentachloride, and total is 14. So the total number of molecules decrease, reactants decrease, products increase. Okay, increase product, that indicates reaction go forward, and the total molecule decrease, and therefore pressure becomes smaller. Okay, what if you want to have a disturbance that decrease pressure by increased volume? So volume increase, pressure must become smaller. So what happens to the reaction? So again, look at the Châtelier principle. The disturbance is decreased pressure, and therefore the reaction will go to the direction try to increase pressure. And again, look at the reaction. If forward reaction molecules becomes fewer and fewer, then the reverse reaction, okay, to the left side, reaction go to the left side will becomes more molecules, because whenever one pentachloride is decomposed, it gives you two reactants, and so more reaction go towards the left side. Okay, as you have seen, to determine how reaction respond to pressure change, we look at the reaction and see how number of moles between reactants and the product change. Note that this must be gas phase number of moles change. So if 1A forms 2B and both are gas phase, then forward reaction increase number of moles, which has the effect of increased pressure. If 2A forms 1B, then forward reaction decrease number of moles, which has the effect of decreased pressure. But if A and B has same coefficient, then there's no number of moles change. Okay, if both are gas phase, then delta N of gas phase is 0. In this case, pressure has no effect because neither direction can counteract pressure change. Now, in the last slide, we show that one way to change pressure is to change volume. If you decrease volume, pressure increase. Okay, but when you decrease pressure, decrease volume, the concentration also change. So it is this concentration change that drive the reaction shift. All right. So because when you change volume, concentration change, and therefore the reaction is not at equilibrium anymore, and therefore it will shift so that the concentration will change until it becomes a new equilibrium. But that doesn't change equilibrium constant K value. Okay, it only changes actually the Q, all right, until a new Q equals K. So change pressure has no effect on the value of K. There's another way to change pressure, and that is you add inert gas. Okay, when you add more inert gas, even though it doesn't participate in the reaction, it increases pressure. However, add inert gas does not affect concentration of reactants and the product, and therefore it has no effect on the equilibrium position. Simple problem 17.12. How would you change the volume of each of following reactions? So volume change to increase the yield of the product. Okay, in the last few slides we show that the volume change has the effect of pressure change, and the pressure change may cause the reaction shift direction. So our plan is we look at the pressure change. If pressure increase, then the equilibrium will shift to lower the pressure. Okay, that's the Châtelier principle. To counteract increased pressure, it will decrease pressure by producing fewer molecules. Okay, the direction will make fewer molecules that will decrease pressure. But a pressure decrease has the opposite effect. So we look at the pressure, find out the pressure, and then we can find the volume change. For example, let's look at the A. Okay, in A, okay, the solid calcium carbonate, so is a solid, so it doesn't count, and calcium oxide or solid doesn't count. So in effect, the gas phase is actually reactants 0, product 1. That's the carbon dioxide. So forward reaction increase number of molecules, which has the effect of increased pressure. Now, our goal is to increase yield. In other words, we want a reaction go forward. Okay. Now, the Châtelier principle says the reaction will counteract the disturbance. So if reaction go forward, that means it will increase number of molecules, number of moles, or it will increase pressure. So if this counteracts the disturbance, then disturbance must be decreased pressure. Okay, so this is the disturbance, pressure decrease. The reaction will respond to go forward to increase number of moles, increase pressure. Okay, so our goal is to increase yield, that is forward reaction. And forward reaction increase pressure, and therefore the disturbance must be decreased pressure. How do you decrease pressure? Increase volume. Okay, and therefore we predict that to increase CO2, we increase volume. That will have effect of decreased pressure. Let's look at B. Again, we want to increase yield of the product, means we want the reaction go forward. And we look at number of moles change. Solid doesn't count. So 3 gas molecule becomes 1 gas molecule. So 3 goes to 1. So if reaction go forward, the number of moles decrease, so which has effect of decreased pressure. All right. According to the Châtelier principle, reaction go decrease pressure is a response to a disturbance that pressure must increase. Okay, this is the disturbance that you increase pressure, and therefore reaction go forward to decrease number of moles, which decrease pressure, counteracts the increased pressure. All right. So how do you increase pressure? Well, reduce the volume, and therefore in B we want to decrease the volume, which has the effect of increased pressure, which will shift the equilibrium to the right side. Now let's look at number C. So number C, all are gases. 1 plus 1 equals 2. So 2 goes to 2. And therefore delta N gas phase is 0. And so in this case, pressure has no effect. You cannot change pressure to change yield. You must find another way to change yield. I want to mention that endothermic or exothermic reactions are not isolated. If a reaction is exothermic to release heat, then the reverse reaction of this same reaction, okay, reverse reaction is endothermic because this product adds heat to the reactants. So forward reaction is exothermic and reverse reaction is endothermic. Similarly, if the reaction is endothermic, the forward reaction is endothermic, then the reverse reaction generate heat is exothermic. We have mentioned that neither pressure nor concentration change affect equilibrium constant. On the other hand, temperature does affect equilibrium constant. Temperature and equilibrium constant are described by this equation called the Van Hoff equation. So this tells you how K changes when temperature changes. So using this equation, you can see here, if delta H is positive, increase temperature, increase K. So K2 will increase. If T2 greater than T1, then K2 is greater than K1. Okay, for endothermic reaction. Now remember, in the last slide, we showed the Châtelier principle says that increased temperature is adding heat. So the reaction favors endothermic reaction because that will absorb heat, okay, to counteract the increased temperature or heat. all right, and therefore it's going endothermic reaction go forward, and that is consistent with this equation, okay, the Van Hoff equation. Similarly, if delta H is negative, according to this equation, increased temperature will decrease K. So again, the Châtelier principle says increased temperature will go endothermic. So if the reaction is exothermic, okay, exothermic, then its reverse reaction will be endothermic. So increased temperature favors the reverse reaction, which decrease the product, okay, decrease K. Sample problem 17.13. How does an increase in temperature affect the equilibrium concentration of the underlying substance and the K for each of following reactions? To study the temperature effect on the equilibrium concentration, we look at the heat involved in the reaction. So we need to rewrite these reactions to show heat as either a reactance or a product based on the signs of the delta H. An increased temperature is equivalent to heat added to the system. According to the Châtelier principle, when you add heat, the reaction will shift to absorb heat, counteracts it, and that is the endothermic reaction. Okay, it will go endothermic direction, and therefore, when reaction go endothermic, the K increase if the forward reaction is endothermic, or the K may decrease if the forward reaction is exothermic. Let's look at the reaction A. Because delta H is negative, that means it's exothermic reaction. The reaction releases heat, and therefore heat should be treated as a product. You add heat as a product. So when you increase temperature, you add heat to the system, the reaction favors endothermic, which is the reverse reaction. Okay, so increased temperature shift reaction to the left. So when the reaction goes to the left, the underlying product substance is calcium hydroxide will decrease, and equilibrium also constant also decrease because reverse reaction consumes product, increase reactants. Okay, let's look at B. Delta H is positive. Positive means endothermic, and therefore heat is treated as a reactant, so you add heat to form product. So when you increase temperature, you add heat, the reaction will favor the forward reaction for the endothermic reaction, okay, absorb heat, okay, and therefore this will increase temperature shift the reaction to the right side, so carbon dioxide, which is underlying substance, will increase, and the equilibrium constant also increase for this forward reaction. In C, the delta H is positive, similar to B, so you add heat as a reactant. It's endothermic reaction. When increased temperature is increased, the reaction favors endothermic reaction, which is a forward reaction. So it go forward, and the underlying substance is reactants will be consumed, and therefore it will decrease. Okay, so the SO2 decrease, but the equilibrium constant increase because it favors forward reaction, increase product, and therefore K increase, but the reactants decrease. We have studied the factors affect equilibrium composition. These are concentration, temperature, and pressure or volume. We show that the equilibrium constant is not affected by concentration change or pressure change. It is affected by temperature. Now there's another factor in a reaction, and that is a catalyst. As you may heard of, catalysts make reaction go faster. It not only increase the speed of the forward reaction, but also reverse reaction. So forward, reverse, both change reaction rate. So in the end, equilibrium constant doesn't change. It makes reaction go faster and take less time to reach equilibrium, but no effect on equilibrium position. Here is a summary of the effects of various disturbances on a system at equilibrium. These disturbances include concentration change, pressure change, temperature change, or catalyst added. As we just showed, catalysts change both forward and reverse reaction rate, but has no effect on equilibrium constant, and there's no effect on equilibrium position. Now, when concentration change, there's no effect on K constant. It doesn't affect the K constant. Only temperature affects K constant. Pressure has no effect on K constant. However, when you change concentration, it does affect equilibrium position. Note the difference. K is a constant, but the position may change. It may produce more product or less product. Okay, depends on the disturbance. So for example, if you increase reactant, the reaction will go forward to the right, because this way it will reduce the reactant. All right, it's according to the Châtelier principle, it will counteract or reduce the disturbance. So increase reactant, reaction go forward to reduce reactant, produce more product. On the other hand, if you decrease reactant, the reaction go to the left, reverse reaction, okay, toward the formation of reactants. Now, when you increase pressure, okay, when pressure changes, to use the Châtelier principle, we need to know the reaction number of moles change. So, for example, A goes to 2B. And so we know the reaction, forward reaction, increase number of moles from 1 to 2. And therefore, forward reaction increase number of moles and has the effect of increased pressure. So if you increase pressure is a disturbance, then for this reaction, it goes reverse, because this will reduce number of molecules, which will reduce pressure, which counteracts the increase of pressure. Okay. Similarly, if you decrease pressure, then for this reaction, it will go forward, because this way will counteract the decreased pressure. It increase number of moles, increase pressure. Now, for temperature dependence, then we need to consider the heat. Okay, if it's exothermic reaction, we add heat. All right, so A goes to product add heat. That's exothermic. If it's endothermic, we add heat to the product. Okay, according to the Châtelier principle, when you increase temperature, that is equivalent to add heat. When you add heat, reaction go forward for the endothermic, because you absorb heat, and that will reduce the disturbance. Okay, if you decrease temperature, then the reaction go favors exothermic, because that will generate heat and counteracts the disturbance to decrease temperature. Sample problem 17.14. For reaction X plus Y2 equals XY plus Y, X is represented by green ball. So this is X, and Y2 is purple, so two purple balls together, that's Y2. To make XY, so here is XY and Y, so this is Y, so these two are product. For this reaction, the question is A, if K equals 2, okay, if we know equilibrium constant, which thing represents the mixture at equilibrium? So this question is not difficult, and all you need is to find Q and then compare with K. If they are equal, then the reaction is at equilibrium. And the next one is where the reaction mixture in the other two things which are not in equilibrium proceed toward the reactant or product. So you are asked to predict the reaction direction. Again, if you know Q, then compare with K, and you should know whether reaction go forward or reverse. And the last one, for the mixture at equilibrium, how will a rise in temperature affect Y2? So this is about a disturbance. Reaction already in equilibrium, and you have a disturbance, and you want to know how that affects reaction. So we just learned the Châtelier principle. Okay, so we are going to calculate the Q and find which one is at equilibrium, which one is not, and then use the Châtelier principle to answer question C. To answer question A, first we need to calculate the Q. Q is calculated by product divided by reactance. Product is xy times y divided by x divided by y squared, or y2. So let's count the numbers of molecules in scene 1. And let's find the molecule X is green. So here is 1, okay, that's all. So you have 1X, and Y2 is purple. So this is Y2, and that's the only one, 2. So you have 1 Y2, okay, and let's look at XY product. So this is a product 1, XY, so 2, 3, 4, and 5. So you have 5 of this one, and the other product is Y. Okay, so here is 1, 2, 3. So you have 3. All right, plug in. So 5 times 3. Okay, product times product divided by reactants 1 times 1, and the answer is 15. So for scene 1, Q is 15. Now you do the same for scene 2, scene 3. You count the numbers of reactants product and you calculate the Q. For scene 2, Q is 2. For scene 3, Q is 1/3. Because K is 2, it's given, and therefore we can see only scene 2 is at equilibrium. Okay, scene 1, scene 3 are not at equilibrium. Let's look at question B. So we already know scene 2 is at equilibrium, and 1 and 3 are not. The question is, will the reaction mixture proceed towards the reactants or product? Now, because Q for scene 1 is 15, which is greater than K, K is 2, so greater than K, that means in the mixture you have too many product compared to equilibrium composition, and therefore the reaction will go reverse to the left side, and that will generate more reactants, consume product. Okay, so it towards the reactants. On the other hand, for scene 3, Q is 0.33 less than 2, and therefore in this mixture you have more reactants than equilibrium composition. The reaction will go forward to the right side towards the product to generate more product. Let's look at question C. For the mixture at equilibrium, and that's scene 2, how will a rise in temperature affect Y2? Okay, to look at the temperature dependence, we need to look at the heat involved in the reaction. Because delta H is greater than 0, a positive delta H means reaction is endothermic. So the forward reaction endothermic, you add heat at the reactants part. So increased temperature means you add heat to the system. According to the Châtelier principle, add heat or increased temperature favors endothermic forward reaction, because this will absorb heat, reduce the rise in temperature, so counteracts the temperature increase. And therefore, we predict the reaction go to the right side. And because Y2 is a reactant, so when the reaction go to the right, it will decrease the concentration of Y2. A very important reaction in industry is the ammonia synthesis. The process is called the Haber process. The reaction is have a negative delta H, and therefore it's an exothermic reaction. In industry, several approaches are used to increase the yield. These are the concentration, the pressure, and the temperature. So in industry, ammonia, the product, is constantly removed. By removing product, the reaction go forward, and so it will produce more product and therefore increase the yield. The reaction is performed under high pressure. Okay, when this reaction, forward reaction, so you can, if you count the number of molecules, in the left side you have 4 molecules, on the right side you have 2 molecules. So if you increase pressure according to the Châtelier principle, the reaction will favor the forward reaction because this will counteract the pressure increase. And therefore that will give you higher yield of the ammonia. And lastly, the reaction is performed under low temperature, and this is because the exothermic reaction. So if it's exothermic reaction, high temperature favors reverse reaction, endothermic, and so low temperature favors the right side, give you better yield. This shows the effect of temperature on equilibrium constant for ammonia synthesis. And because this reaction is exothermic, okay, so according to the Châtelier principle, high temperature, increased temperature favors endothermic, and that will be the reverse reaction, and that will decrease K constant. So high temperature, low K, small k, so 10 to the minus 2, and low temperature, large K constant. So increased temperature causes equilibrium to shift towards the reactants. This shows how pressure affects the yield of ammonia. So if temperature is fixed, let's say 400 degrees, and if pressure is 10, the percentage yield only 5% at low pressure. Increase pressure to 100, the yield goes to about 27. Okay, if you increase to 300 atmosphere, you got 50% yield. Okay, so increase pressure, increase yield. Here shows the key steps in Haber process for synthesize ammonia. And you add hydrogen gas, nitrogen gas to a compressor. The compressor compresses the gas to a high pressure, so you increase pressure. And in the reactor, you add a catalyst. So here you have catalyst to increase reaction rate, and the reaction is done at high pressure. So after this stage, you get a mixture of product ammonia with some unreacted hydrogen and nitrogen. Then the mixture is subject to cooling. So when it's cooled, the ammonia will be condensed into liquid. So in this stage, some ammonia becomes liquid, and the liquid ammonia is separated from the gas phase hydrogen and nitrogen. The gas phase hydrogen and nitrogen go back to the compressor, and the product constantly removed from the system. And then you add fresh nitrogen hydrogen compress and let the reaction proceed. So you get high yield of ammonia. Please read the textbook, go over lecture notes, practice follow-up problems, and work on both homework 1 and homework 2.